Okay, here's part 2 of the video lecture for General Physics 2 for Monday, the 30th of March. So we're going to do an example. This is the example that we're going to do. We're looking at what the magnetic field is at point P. It's actually 0. And we have a 10 amp current going through a wire, which is 8 centimeters away. We're neglecting the diameter of the wire in our calculation. And we want to know what the current is in the wire that is 4 centimeters away, what direction it's moving, and what the magnitude is. Okay, so the first thing that we need to understand is in order to cancel out the current in the top wire, the current in the bottom wire is going to have to go in a different direction. If we use the right-hand rule for the top wire, that would mean that the magnetic field at P would be going into the page. So in order to cancel that out, we need to have the current going in the opposite direction, or the magnetic field for the second wire going out of the page. Okay, so we know that the current in the bottom wire has to be going to the left, right? It can't be going to the right. So it's either D or E, 10 amps to the left or 5 amps to the left. Okay, so let's go ahead and do the calculation. But what we're going to need to understand, first of all, is what's our governing equation. We go back to this page, and our magnetic field is going to be just our permeability constant times our current times 2 pi, and R is the length that is from the wire that's carrying the current. Okay, so we're going to solve that for two different currents, and our magnetic field at that point is 0. Okay, so let's switch over to the document camera. Okay. See if we can go ahead and do this. Okay, so what we have, we'll just wait and make sure it gets into focus here. Always fun to play with technology, see if we can focus it. Okay, that's not quite in focus. We'll see if I can work my magic here. There it goes. Okay, so we have a wire. Our current is 10 amps. Okay, another wire. And we've established that the current is going in the opposite direction just by inspection. And we need to know, what the current of that wire is. Okay, the dimension here is 4 centimeters. And the dimension here is 4 centimeters to point P. And the magnetic field at P equals 0. Okay, so our magnitude and our direction of our magnetic field are equal to 0 at that point. Okay, so we go back to our governing equation. There it is. Okay, so we know that our magnetic field at this instant, okay, is actually B is the sum of all mu sub O I 2 pi R going in specific directions. Why is that not focusing again? Focus. Okay, it's trying hard. Okay, then move down the page a little bit. Okay, so we know that B equals 0 equals mu naught I sub 1, that's for the first wire, divided by 2 pi R sub 1, that's why the first wire, and then that's mu naught I sub 2, that's what for the second wire, 2 pi R 2 for the second wire. Okay, and all that is equal to 0. Okay, so we can go ahead and distribute terms here. We know that mu naught and 2 pi are just going to be collected, so we can just write it like this: mu naught divided by 2 pi times I1 over R1 plus I2 over R2 equals 0. So when I do that, just using algebra, then I know that I can just cancel this out because anything times 0 is equal to 0. So I can cancel out that term. And then down here, I'll just rewrite this, that 0 equals I1 over R1 plus I2 over R2. Okay, so I just plug in my numbers. I know my current, I1 is 10 amps, R1 is 8 centimeters, so that's 0.08 meters, plus I2, and R2 is 0.04 meters, that's just 4 centimeters. Okay, and then I can solve for I2. So I go ahead, set that equal to 0. And when I do that, then I can just say that, I'm sorry, I apologize, I'm left-handed. I'm always covering up the page with my hand. Okay, so I can just go ahead and then say, just rearrange that, 10 amps over 0.08 meters equals negative I2 over 0.04 meters. Okay, so I've just taken this particular step here. Okay, and then for the first page, then that would just mean that I2 is equal to negative 10 amps divided by 0.08 meters times 0.04 meters. Okay, and then I calculate that out. And my dock camera is just a little crooked. And so that gives me I2 is equal to negative 5 amps. And that negative sign there, all that means is that it is going in the opposite direction of the 10 amps. So so it's indeed 5 amps to the left, not 5 amps to the right. Move that out of the way. Then we go back to the lecture notes. Okay, rid of the dock cam, it's in the way. And so we know, and when we go back to this problem, that the answer is E, 5 amps to the left. Okay, so let's look at some further equations for the current loop and the solenoid. Okay, so when we do this, we have a current loop. You want to draw it in the plane of the paper, okay? So you have a loop here, the current's going out of the paper and then back into the paper. You flip around the paper, and then at the top, the current is moving towards you. At the bottom, the current is moving away from you, okay? Then when you want to get the magnetic field, then you just use the right-hand rule. With the right-hand rule, then you're just taking the loop and pointing your thumb in the direction of the current, which is out of the page towards you. And that gives you the direction of the magnetic field. If we did down here, then your thumb would go into the page or away from you, and the magnetic field would move in the opposite direction. But again, from the center, then the magnetic field is moving from left to right, okay? If we had the loop in the page itself, then the magnetic field in the center would be going out of the page toward you, and then outside would be going away from you into the page. Okay, so let's say we have this magnet here, and it shows a current loop that's perpendicular to the page, and we just see a slice of the current loop. Okay, the current direction of the current in the wire, the top is going towards you, and the bottom is going away from you. Okay, then what is the direction of the magnetic field pointing to the center of the loop? So what you want to do is you just take the top right-hand rule, okay, and all that's doing is then you're curving it around. And when you use the right-hand rule and curve that around, then that's going to tell you that the current is C, going through the magnetic field, excuse me, is going to the right. Okay. So let's say we switch this around. We have two adjacent current loops, and they're going to exert force on each other. And think about the force that's exerted on the loop to the right, that's this loop, due to the loop on the left. Okay, so the force is going to be in the direction of the magnetic field. Okay, and the force, so if we look at this, then the current at the top is going into the page, current in the bottom is going out of the page, and so that would then use the right-hand rule going into the page, then the magnetic field is going to be going towards the right, or excuse me, towards the left, okay, because we've switched around the current in our loops. Okay, so the direction of the force in this loop is going to be actually going towards the other loop or to the left. Okay, now when you have a solenoid is just many, many loops of current all put together. You have a single current going through the wire, and by including loops on the coil, and that's going to increase the strength of the magnetic field multiplied by how many coils you have in the loop. Okay, so in a loop like this, the current is at the top is going towards you, current at the bottom is going away from you. So that's going to create an incredible amount of magnetic force that's going to go from left to right, has to squeeze through. And inside the solenoid itself, you can assume pretty much that the magnetic field is going to be constant. Okay, so here's the solenoid, okay. And the direction of, you want to know the direction of the current of the solenoid, okay. And here we've got a current loop, and the magnetic field is going towards the top. So we use the right-hand rule, okay, and we grab our fingers now are going up, and when we use the right-hand rule, then the current is actually moving from the top to the bottom, okay, and so if it's moving to the top, from top to the bottom, it's actually going counterclockwise. Okay, so now I'm going to give you some more equations so we can do some more examples. Okay, here's the magnetic field for a current loop. Okay, so if you have a current loop, then this in the center of the magnetic field B is going to be the permeability constant times your current divided by 2 times the radius of the loop itself. If you have multiple turns in your coil, turns that you have in your coil. Okay, so our magnetic field will increase in strength arithmetically by the number of coil loops we have in a particular coil. Now, if we have a solenoid, then the solenoid, usually you don't necessarily know the number of turns. Or, I'm sorry, you do know the number of turns, but you just take the number of turns and you divide it by the total length of the solenoid. Okay. Direction again is given by the right-hand rule. Okay, so let's do a few examples. Okay, and I think at this particular point, actually, why don't I just pause this, and then I'll just do the example on the doc cam, just going through this directly. Okay, so let's pause, and I will be right back. Okay, so here's the first example. We have a physics instructor, and they want to create a demonstration that shows the direction of the magnetic field, and they're going to use a current loop. We're going to calculate this as a current loop and not a solenoid. And he's got a cardboard form. Yeah, actually, we're given enough information. We can, we can calculate this as a current loop. So we've got a cardboard form that is 25 centimeters in diameter, and it's got an N of 20 turns of a wire. So he wants a magnetic strength to be at least 10 times as large as the magnetic field of the Earth. So the compass will be pointing to the direction of the field in the loop and not with the Earth. So we want to find I, the current that's needed to provide this. So what we need to do is go back a few pages. Okay. And here is our equation. B is equal to our permeability constant times the number of turns times the current times 2 times the radius. So that's our governing equation that we want to use. So we go back to our example problem. Okay. Let's switch over to the doc cam really quick. Okay. And so we have N equal to 20 coils. The diameter is 25. I'm going to have to double check on that, so I'm going to go back to this really quick. 25 centimeters. Okay. All right, that seems big to me. That is, okay. So our radius R is equal to 12.5 centimeters. Okay. It's not focusing, so we'll try it again. There we go. Try to focus. Okay. And we know that our magnetic field is equal to the permeability constant times I. I'll cheat and go back and look again. Times Ni divided by 2R. Okay. 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 So we know that B for the Earth, I looked this up in the book, is 5 times 10 to the negative 5th Tesla. Okay. And so our B is going to be 10 times that. So B is going to be 5 times 10 to the negative 4th Tesla. Okay. Our permeability constant, mu sub O, is 1.257 times 10 to the negative 6 Tesla meters per amps. Our radius, we know already, is 12.5 centimeters. Our number of coils is 20. So we can just solve for I. So I equals B times 2 times R divided by mu sub O, our permeability constant, times N. Okay, so we just go ahead and plug in numbers here. 2 times our field strength, which is 10 to the negative, 5 times 10 to the negative 4th Tesla, times the radius, which is 0.0, or excuse me, try again, Brian, 0.125 meters divided by our permeability constant, which is 1.257 times 10 to the negative 6 Tesla meters per amps, times the number of turns in the coil, which is 20 turns. Okay, so I'll just carry this down here. Go ahead and use our calculator to calculate this. Okay, and that flips around. So I just take 2 times 5 times 4 negative 10 to the, okay, times 0.125 meters divided by 1.257 divided by 6 negative 10, okay, divided by 20. Whoops. I'll see a little bit. Okay, and that gives me 4.97 amps. Okay, so the current that it needs to go through for that particular problem is 4.97 amps. Okay, so let's do another problem. Okay, let me switch to the PowerPoint. Okay, and we'll go to the second problem. Okay, I'm doing these cold, so give me lots of grace. Okay, an investigator needs a uniform 30 millitesla field, which she intends to produce using a solenoid. She takes a long 10 centimeter diameter tube and wraps wire around the length of it, wrapping 1,200 turns of wire along a 75 centimeter length of tube. how much current must she pass through the wire to produce the desired field? Okay, so we're going to go back again. So now we're using the equation for a solenoid. Which is our magnetic field is equal to our permeability constant times the number of wraps on the wire. Okay. Oh, wait a minute. I'm doing a solenoid. Never mind. Okay. Is our permeability constant times the current times the number of wraps in the wire divided by the length. Okay, so diameter doesn't make any difference here. It makes no difference. So we're going to go ahead and back solve that for current I. Okay. Go ahead and switch over to document real quick. Okay, so that's the number of wraps divided by the length. Get that in focus. It is not focusing. Sorry, everybody's looking at this video and getting car sick because we can't focus it. Okay, so we're going to solve for current I. So current is just equal to B times the length of the solenoid divided by the permeability constant divided by the number of turns in the wire. Okay, so when we do that, it's going in and out of focus, and I do apologize for that. Just doesn't like to focus very much. Okay, so when I do that, then I know that going back to the problem here really quick, we have 30 millitesla field. We have 1,200 turns, that's N, 75 centimeter length, that's L. Okay, and so now we have enough information to solve for the current. So we go back to the doc cam, and we know that B is 30 millitesla, which is 0.030 Tesla. Okay. We know that our length is 75 centimeters, which equals 0.75 meters. And our number of turns in is equal to 1,200 turns. Okay. So then we go ahead and put in all of our information below. Okay, actually, I'll just put it right here. So we have 0.030 Tesla times the length, which is 0.75 meters, divided by our permeability constant, which is 1.257 times 10 to the negative 6 Tesla meter per amp. And then the number of turns, which is 1,200. Okay. And then we just do a little dimensional analysis. Teslas cancel, meters cancel, and that leaves amps in the denominator of the denominator. So that will leave amps in the numerator. Okay, so then we go ahead and calculate this out with your calculator. So we have 0.030 Tesla times 0.75 meters divided by our permeability constant divided by 1.257 divided by 6, negative 10 to the 6. Okay. And then we divide that by N, which is the number of loops in our solenoid, which is 1,200. And that gives us a current of 14.9 amps. So I is 14.9 amps. Okay, so that completes that particular example. Okay, we can go back to the PowerPoint. Okay, and we have another example problem. I think what I'll do, let's see, what am I going to do? Okay, let's do this other example problem really quick. We'll make this second lecture a little long, but let's say I have a current loop here. Make this bigger. Okay, current loop. My current is 3 amps, and it is moving around in a clockwise direction. okay? And we want to know what's the direction of magnitude of the magnetic field at point P in the center of the loop. We have a radius of 4 centimeters. Okay, so let's go back to the governing equation. First of all, we use the right-hand rule to tell us that the current itself, okay, the way that it's moving around, okay, means that P itself, when we use the right-hand rule, is going into the page. Okay, so it's going into the page. It's not going out of the page. You want to take your thumb, and on the right side of the coil, you just take your thumb, point it down, and that wraps your fingers into the page. If you move to the left side of the page and up, then it also wraps your fingers around and into the page in the center. Okay, so we know the direction. Now let's find the magnitude. So we go up a few slides. Okay, and if we have a single loop, then current B, or magnetic strength B, is equal to our permeability constant times our current divided by 2R, radius. Okay, so we go back to our example problem. Okay, then we switch to the doc cam, write down some of our information. Whoops, doc cam, there we go. So we know that B is equal to our permeability constant times our current divided by 2R. Okay, so we know that our current I is equal to 3 amps. Okay, I'm just going to double check real quick. Yeah, 3 amps, okay. Our radius R is equal to 4.0 centimeters, which is 0.040 meters. Okay, and then we have enough information to solve the problem. So B is equal to 1.257 times 10 to the negative 6 Tesla amp meters per amp. Okay, then